Last time we proved Blumenthal's 0-1 law, which is the statement that for strong Markov processes like Brownian motion, the augmented sigma field for the natural filtration at time 0 is trivial. All events in that augmented sigma field have probabilities 0 or 1. That's going to have profound consequences for the behavior of Brownian paths near the starting time, and by the time inversion symmetry of Brownian motion, also near infinity. Here's the result. Let Bt denote a Brownian motion on the real line. Let's look at three important times associated to the behavior of the paths at time 0. T0 is the infimum over all strictly positive times where the Brownian motion is 0. Of course, we know it starts at 0, canonically here, but if we look at all of the times later on, if there are any, when it hits 0 again, let's look at the smallest, or at least the infimum, among those. Similarly, T plus will denote the infimum over all positive times where the Brownian motion is strictly positive, and T minus is the infimum of all strictly positive times where the Brownian motion is strictly negative. The result is that starting at 0, all three of these times are 0 with probability 1. That seems very strange. How can that possibly be? Well, what it means is, here, that the Brownian motion is 0 infinitely often in any neighborhood containing 0, which suggests that maybe the Brownian motion starts off just being flat 0 before it leaves. Well, no, that's not the right explanation, because T plus is also almost surely 0, which means that there's also, in any neighborhood of time 0, points where the Brownian motion is strictly positive. And similarly, in any neighborhood, there are points where the Brownian motion is strictly negative. So what that says is that Brownian paths have to look like this. Whatever they do, when they leave 0, they hit 0 again infinitely often, at least for a little while also oscillating above and below. Brownian paths are rapidly oscillating near 0. And by the strong Markov property, as we'll explore in the next lecture, that means that they are rapidly oscillating everywhere as well. Now, to see why this is true, we simply note that T0 here, this is the hitting time of the set 0 for Brownian motion. 0 is a closed set, and Brownian motion is a continuous path process, and therefore, as we showed earlier, this is an optional time. Similarly, T plus and T minus are the hitting times of the interval from 0 up to infinity and the interval from minus infinity up to 0 open. Since those are open sets, we only even need to know right continuity of paths to show that these are optional times. Since they are optional times, by definition, the event that T plus, T minus, or T0 are equal to 0 is in the augmented sigma field F0 plus. Remember, an optional time for the original filtration Ft is the same as a stopping time for the augmented filtration Ft plus. And while we don't usually deal with tau equal T type events, we could rewrite these as the event that tau plus is less than or equal to 0. And so this exactly fits the mold. So these are in F0 plus, but by Blumenthal's 0-1 law, that means that the probability of each of these events is either 0 or 1. So all we need to do is show that they're not 0. And to show that they're not 0, we just need to show that they're greater than 0. But that's not so hard to do. Let's start by looking at T plus. For any strictly positive time, if I look at the event that Bt is greater than 0, that's going to be contained in the event that T plus is less than or equal to T. Because T plus is the infemal time where Bt is positive. And so if T is a time where B is positive, that means that the infemal time is less than or equal to T. But for fixed T, Bt is just a centered normal random variable of variance T. And so that says that the probability of this event here, well, that's exactly equal to 1/2, because Gaussian random variables are symmetric. And so that says that the probability of this event is greater than or equal to 1/2 for all T. But then the probability that t plus is equal to 0 is the limit, as n goes to infinity, of the probability that t plus is less than or equal to 1 over n, since those events decrease to the event that t plus is equal to 0. And since each one of these is greater than or equal to 1/2, that shows that this limit is greater than or equal to 1/2. And so by Blumenthal, that tells us that this probability is actually equal to 1. We can make an entirely analogous argument for t minus, or we can use the fact that t minus for the process B is the same as t plus for the process minus B. And as we've already shown, minus B is also a Brownian motion. And then finally, for t0, we just note that the event that t plus is 0 and t minus is 0 is contained in the event that t0 equals 0. That is, if there are arbitrarily small times when the process is positive and arbitrarily small times when the process is negative, then there must be arbitrarily small times in between them where the process is 0, because the paths are continuous and we have the intermediate value theorem from calculus. And so that proves this result. So the triviality of F0 plus is not a trivial matter at all. It tells us amazing things about the rough paths of Brownian motion. And now let's use time inversion symmetry of Brownian motion to show similar properties for the behavior of the paths as t goes to infinity. If bt is a Brownian motion, look at these three comparable times to the t's. S0 is the largest time where bt is 0, and s plus and s minus are the largest times where the process is positive or negative, or at least the supremal times. Then each of these is almost surely equal to infinity when the process starts at 0. Actually, it doesn't matter if we start at 0 for these statements or not. The proof here leverages what we proved on the last slide, just together with the fact that the process xt, defined by t times b1 over t when t is greater than 0 and 0 at time 0, is another Brownian motion. That means that tx plus or minus and tx0 are all 0, almost surely, as we showed. Well, the event that s0 equals infinity is just the event that bt equals 0 infinitely often as t goes to infinity. But given the relationship between bt and xt, and the fact that this t out front is strictly positive for all strictly positive t, this is the same as the event that xt equals 0 infinitely often as t goes down to 0. But that is exactly the event that t0x is equal to 0, which we've shown has probability 1. And s plus and minus are entirely analogous. So Brownian paths oscillate wildly as the process leaves 0, and they also oscillate forever, crossing 0 infinitely often as you go out, but being positive and negative infinitely often as we go out as well. As we've seen, the size of those paths grow in lim super lim inf at approximately rate square root of t, or a little bit more. So the paths are growing in size but always oscillating back and forth, while they're also on a local scale oscillating rapidly for all time. These are more qualitative demonstrations of how rough Brownian paths are. Now we'll be able to make even more quantitative precise statements about the behavior of those paths on large and small scales by further applications of the strong Markov property. And to do so, we now turn to a hallmark result of Brownian motion, the reflection principle.